Dealing with uncertainty and addition and subtraction is rather straightforward. Just have to keep a couple of common sense things in mind. So we can't reduce the uncertainty, so of course we're going to have to sum the uncertainties in each of these, even if you're subtracting. So in the top one we just go 2.6 plus 2.8 to the 5.4, and then we add the uncertainties to get 1 centimeter of absolute uncertainty. We just leave them in absolute uncertainties for addition and subtraction since we can just sum them so simply. And here it's the same procedure, 2.6 minus 2.8, and then we add the uncertainties together. Just notice that the units have to match across the value. You certainly can't have your 2.6 in a different unit than the 0.5. Also, you can't claim to know your error to a higher precision than your value. So if the 2.6 is only known to 1 decimal place, you certainly can't have more than that over here. It would boggle the mind otherwise to how you actually got that error measurement and why you didn't have more precise measurement on the other value. Okay. That's addition and subtraction. For multiplication and division, we'll see here it's a little bit more complicated because instead of just doing the absolutes, we have to do it relative to the value itself. So it's only one more step, and it's a rather simple mathematical step as well. There's no difficult calculations dealing with error. It's just changing it to a percentage. So 0.5 divided by 2.6 times 100% will give you the percentage of the error compared to the 2.6. Same thing over here with the 2.8. And then after that, it's just the same procedure as before. You do the 2.6 times 2.8, so this value times this value. And down here it's the same thing, but you're dividing them. And then you take your percentage errors, so you have 19.2% on the 2.6. This turns out to be 17.8% on the 2.8. And we just sum those. Again, we can't reduce the error, so it always has to add. Gives a rather high total, it seems like. And then you take this percentage and you apply that to the value you get after your computation. So you apply the 37% to the 7.3 here, and here you get the same 37%, and you apply it to the 0.93. Notice that if you're using the same numbers over again, you don't have to redo these steps. Just save yourself some work. You've got the percentages already calculated up here, so you just copy them down. The next thing is averaging. If we have repeated trials or repeated measurements like this one, which I think is from a micrometer, then you can calculate the mean to represent the overall number of trials you had. So you just calculate the mean like usual, add them up and divide by how many there are. That turns out to be 5.825 in this example. But for the error, again, we can't play any tricks with our error, we just have to be honest about it. The worst error is this one. So that's the error that turns out being in our answer. You can't just choose the least amount, or you can't average the errors because then again you're losing some error. You can never lose your error once it happens. You have to avoid it experimentally. You can't deal with it computationally and make it less. When you're dealing with powers, this is something you should be able to figure out just by how we had to deal with multiplication. If I squared is in this formula here, P equals I squared R for power, then of course I squared means I times I. So if you have I times R, you're going to have to take each of the absolute errors for each of these three factors, and you're going to have to change them into percentage errors, as we showed earlier, and then add them together. So you'll have 3 things to add rather than 2. If you're not looking very carefully, you may have thought you only had to add 2 errors together, but there are actually 3 things being multiplied here. Now, if this is a higher power, you're not going to want to sum repeatedly so many times, so instead, of course, we just use multiplication. I can take the 2 and multiply it by the percentage error for I, and then add in the percentage error for R. And of course, that would come to the same thing as adding twice instead of multiplying by 2. So if it's a higher power, we would just multiply the higher power by the percentage error for I. If you have other functions than addition, subtraction, multiplication, and division, then then all we can do then is report the range of possible answers. So in this case, we have the sign of 0.8 plus or minus 0.1. So the lowest value we could have here is 0.7 and the highest is 0.9. If we find the sign of each of those, then we get a range that we can use to report our final result. We have no reason to believe any particular value is the proper one. Anything in that range is possible. Okay, when you're dealing with all these things, then it's good to keep in mind this rule of thumb. If one uncertainty is much larger than the others, then the others can be ignored in calculation and reporting of the error.